Hello, this is our presentation on habitable exoplanets. This is our table of contents, which covers habitability requirements, habitable exoplanet discovery, potentially habitable exoplanets, and our conclusions on this topic. So, what makes a planet habitable? As of we know right now, Earth is the only planet that's able to host life, which pretty much sets it as the standard reference when searching for other habitable planets, and that's where this criteria comes from, which covers three crucial aspects, being stellar flux, the star's radiation, the planet's composition, and the planet's atmosphere. The stellar flux can essentially be can also be identified as the Goldilocks zone, which is basically the idea that there's a certain area or distance from the star that's considered to be habitable. In this case, this area is not too hot or nor too cold for water to exist, but it can also depend on the type of star. Which would affect its distance from it. Another thing that a planet needs to support life is it needs to have a rocky surface, some geological activity, and most importantly, water. The rocky surface should be able to provide minerals. There should be activities such as the moving of plate tectonics, which should be able to recycle things into the atmosphere. And another thing is that the seas can also act as climate controllers, since they can absorb 90% of trapped heat and carbon dioxide in order to regulate the climate, provide a solvent for chemical reactions, and monitor the carbon cycle. In order for a planet to protect itself from having a stripped atmosphere, it should be able to have a strong magnetic field, which basically protects it from solar flares and solar winds. The planet's rotation pretty much determines its day and night cycle, which actually has a significant effect on its ability to sustain life. Since having a stable rotation means having stable temperatures and a strong magnetic field, Furthermore, having a stable rotation around the star is also needed for a planet to be habitable year-round. Next, energy sources like light from a star and geothermal heat are mainly transferred to living organisms, either through photosynthesis or chemosynthesis, mainly the star is a key aspect of this process, because it has to be able to provide enough energy to sustain life, meaning that the star cannot really be violent, because it'll have frequent solar flares that would damage the atmosphere. And lastly, for a planet to be able to sustain life, it needs to have the right amount of oxygen, because having too little oxygen will not allow for complex life forms to exist, but also having high levels of oxygen will become toxic to the cells of those living organisms. And yeah, as a reference, the Earth's atmosphere has about 21% of oxygen. And besides oxygen, plants also need to have other gases like nitrogen, carbon dioxide, methane, water vapor, and argon, because they'll be able to dilute that oxygen, trap heat to maintain stable temperatures, and block harmful radiation.
So I'm going to be talking about habitable exoplanet discovery and how kind of scientists find exoplanets, habitable ones. So there are two main methods. One is the transit method, as one is the radial velocity method. I'm going to be going through both. So the transit method, also known as transit photometry, detects exoplanets by monitoring a star's luminosity for quick, regular dips in brightness. And these dips in brightness are caused by an exoplanet crossing directly in front of its host star along our line of sight, blocking a small amount of the starlight for a small length of time, like a miniature eclipse. Like the exoplanet rotates between Earth and the star, and so it blocks a bit of the star's light that we see. So by measuring the star's light over and over, scientists create a light curve graph. This is observed in the image as the brightness sharply drops as the exoplanet crosses the star. And because the decrease in light is directly proportional to the planet's size to the star, physicists can derive the radius of the planet, but only the radius and the orbit, which leaves the mass unknown with the transit method. So the orbit. To find the orbital period, or the length of the exoplanet's year, scientists wait and monitor these dips in brightness repeatedly, And the orbital period is the amount of time between the two dips in starlight. And so that's right there is how we find the length of the exoplanet's year. And because planets orbit their stars at a constant speed, these dips will repeat at regular intervals. So once the orbital period is determined, scientists can explain the exoplanet's size and distance from the star. First, the radius of the planet is determined by how deep the light curve is in the graph. I already mentioned that. Bigger dips means bigger exoplanets. Smaller dips would mean smaller exoplanets. And secondly, by taking the orbital period and applying Newton's version of Kepler's third law, which is seen bottom left, um, scientists can calculate the planet's orbital distance, which is how far away it is from the star, seen in the figure. So, the second method, the radial velocity method. This method finds an exoplanet by using the Doppler effect, which is basically a star's gravitational wobble. So, because of mutual gravitational attraction, which is basically meaning that a star exerts as much gravity on a planet as the planet does on the star, a star and its orbiting planet revolve around a shared point called the common center of mass. So, basically, a star doesn't just rotate kind of in place, it has its own little orbit, which is very small, and it rotates around the common center of mass, which is a point located just inside or outside the star's surface. And the exoplanet also orbits this. So as the planet loops around it, its gravity tugs at the star into like a little tiny counter orbit. And when the star wobbles towards Earth, the light that the star translates is blue shifted. And as it moves away, the light stretches into a red shift. And then scientists track these shifts and by watching the absorption lines in the light spectrum from the star. And they can calculate the star's exact speed using the Doppler effect formula, which is up on the top image. So the atmosphere plays a huge role in a planet's habitability. So to find the atmosphere, scientists use transit spectroscopy. So as the exoplanet crosses the star, a tiny amount of starlight from the star filters through the planet's atmosphere of gas. Because different gas molecules like water, carbon dioxide, methane, etc., they all absorb specific wavelengths of light. They leave absorption lines in the star's light spectrum, which then can be picked up and compared, and we can find what is missing in the light spectrum, which allows us to identify the gases that make up the atmosphere. So the primary tools that are being used for exoplanet discovery is the NASA Transiting Exoplanet Survey Satellite, or the TESS, and it monitors all objects change in brightness, like in the sky, and it has provided us with the most complete view of the starry sky that we have to date. We also have different space telescopes, such as the James Webb and the Kepler, and they use spectrographs which analyze the starlight passing through the exoplanet's atmosphere, as I mentioned before, to find out an atmospheric composition.
Hello, this is Aaron, and my section is on potentially habitable exoplanets, which real planets that we found could sustain life. Okay, so how do we find specific details about these exoplanets? Basically, once we use the methods that we previously talked about, we could find the exoplanet's size, orbit, mass, and a rough estimate of what its atmosphere looks like. And once we have all of those, scientists can make a rough guess of what a planet looks like. But once a planet's about 50 to 100 light years away, we can't reliably estimate what its atmosphere looks like. So anything beyond that, take it with a grain of salt. So what makes an exoplanet good for life? What makes it a good candidate? So of course it needs, as said in section one, it needs a good and stable position. It needs to be in the Goldilocks zone. It needs to be in an area where it gets sufficient energy, but not enough to overkill any life. And then supports, does it have a reasonable composition? Like, is it rocky? Does it have an atmosphere? Does it have the necessary gases? Is the planet similar enough to Earth where it can exhibit similar qualities that can make life thrive? And then we'll touch on this later on. Can that exoplanet be colonized in the far future? Okay, so how am I deciding which planets I'm including here? Mainly, I'm using their similarity with Earth and their qualities that could support life. And then for Earth similarity, I'm using the Earth Similarity Index, or ESI, which measures the planet's radius, density, velocity, and surface temperature in relation to Earth's, basically how similar it is to Earth. And then beyond that, I'm also considering the star of the exoplanet, how interesting it is, like how fun it is, and whether it could support an atmosphere. Here are some quirky honorable mentions. We have Proxima Centauri b. It's very close, but it's unstable. Kepler 186f. It's the very first exoplanet found in a habitable zone. Wolf 1069b was it's a rocky and tidally locked exoplanet, so only one side sees the light and one side's permanently in the dark. And then Gliese 667cc. It's part of a triple star system, and it can support water. So here's my top five. Here's Kepler 442b, has a 0.84 in the ESI. It's estimated to have good plate tectonics and a thick atmosphere for life. It has less UV radiation than Earth, and it has a very reliable orange dwarf star, which could potentially make it better for life on Earth, but it's very far away, so we can't verify much about it. LHS 1140b, it would be a massive Earth-like planet, and it's only 48 light years away. It has a very low Earth similarity score, but it's hypothesized to have a lot of water. If it could support it, we don't know much about its atmosphere. It's very cold, so most of this water would be in the form of ice. TOI 715b, it was discovered by NASA. It's about 138 light years away, and it's about 80% similar to Earth. It's kind of like a super Earth, and it would have a strong magnetic pull, which would give it a high chance to have an atmosphere suitable for life. It would have retained a lot of its gases. T Garden Star B, this is number two, has a very high Earth similarity score. It's probably what I think would be the first planet to be colonized. It has a very suitable temperature for water at 82 Fahrenheit. And number one on my rankings is TRAPPIST-1e. It has a very notable atmosphere and is currently being researched by the James Hubble Telescope. It kind of has a low ESI, but it has also a small mass. What makes it super interesting is that it's right in the middle of its ultra cool red dwarf's habitable zone. Studies think it has a Earth-like composition and strong gravity, which makes it a very likely candidate to have held on to the gases, which would give it a habitable atmosphere. And it's also only about like 41 light years away. So now that we've learned about exoplanets, why should we care? Well, a big reason is space colonization. Maybe in the future Earth may no longer be habitable. Think of Interstellar. We could support excess human populations. Maybe we could use it as an extraction colony, and then yeah, just be cool to colonize other worlds. And look at the Artemis missions. NASA wants to establish a semi-permanent base like infrastructure on the moon by 2029, which would be a huge step in colonizing other exoplanets that could be colonized in the future. So how far will we go? Thank you all for listening.